Good morning, participants. Today we have our speaker, Dr. S. Murthy. Sir will deliver a session on influence of IoT in Industry 4.0. Dr. S. Murthy, currently working in National Institute of Technology, Tiruchirappalli. He is a postdoctorate in reconfigurable architectures from KIT Royal Institute of Technology, has over 18 years of experience in teaching and research. Sir has received Young Faculty Research Fellowship by FRF Award under MITE, Government of India in January 2018. Dr. S. Murthy has completed 2 research projects and 1 research project is ongoing, has published 5 patents, has guided 40 UG projects and 30 PG research projects. Coming to the publications, Dr. S. Murthy has published 31 international journals and 1 national journal and 32 conference presentations and publications. Today, Sir will handle a session on IoT and its influence in Industry 4.0. Over to speaker.
Good morning, all of you. Am I audible?
Yes, sir. You are audible, sir. Screen is also visible.
Yeah, thank you. Okay. So, it is a great pleasure to be part of this ATAL workshop organized by IIIT Trichy. In fact, this is the first interaction I'm having with IIIT Trichy after coming into NIT Trichy campus. This is the first time. Technically, I'm having an interaction with them. So today we'll be looking at the Internet of Things and its influence on Industry 4.0. The main motivation behind having this topic, especially for the say teachers or researchers who are working on electronics and communication engineering field, is to stress that what are the avenues that are available for the ECE researchers to work towards IoT applications on electrical engineering. This lecture would say more about where and all the impact of ECE is on electrical engineering and automation. So with this small introduction, let me tell about the contents. So I'll be talking about, first I'll talk about Industry 4.0. What is the, what is the use of Industry 4.0? Then what are the challenges faced by Industry 4.0? And the components that influence Industry 4.0. Then we'll be looking at the use of IoT in the development of Industry 4.0. Then what are the contents of IoT? Then we'll be looking at different applications related to IoTs, and that will really aid the Industry 4.0 concept. So these are the contents which I have planned for this lecture. When we get into Industry 4.0, before getting into Industry 4.0, we have to see the sequence of Industry 4.0 and how it got evolved. So in a very early days, we had this Industry 1.0 where they mostly concentrated on mechanization, then steam and especially on steam and water power generations, and they worked more on the mechanical component development. And after that, in Industry 2.0, they concentrated more on mass production. And to be very specific, the electrical power production was concentrated more, and they started, exploring more different types of electrical power production, and they standardized it in Industry 2.0. And when we get into Industry 3.0, electronic and IT systems and automation came into much of the concentration, and we could have seen this electronic and IT systems and automation. See the impact of electronic and IT systems and automation for the past 20 to 30 years. We would have seen its impact very clearly, and its growth also. So now we have Industry 4.0, which concentrates more on cyber physical systems. So the integration of electronics along with the IT and automation together for certain, for different applications, we call here as a cyber physical system. It is going to be merely again an automation and remote online monitoring and control. These are certain aspects which are concentrated on Industry 4.0. When we see Industry 4.0, as such, it is a fourth industrial revolution, which encompasses the areas which are not normally classified as industry. This is the very, very important point to be noted for Industry 4.0. So it not only concentrates on industrial area, it also concentrates on the other areas which are not normally classified as industry. So example here is a smart city. So you might have heard in the recent days what would be the concentration of smart cities in all over India. So not only in India, in all over the world, you could have seen it. Especially in India, you can see that what would be the concentration of the government on developing the smart cities. So this Industry 4.0 clearly refers to the concept of factories in which machines are augmented with wireless connectivity and sensors connected to a system that can visualize the entire production line, control, and make decision on its own. So it starts with with the help of certain sensors, which senses the actual physical state and communicates to the controller, and it might be even through a wireless connectivity, and the values which are sensed, the physical state which was sensed by different types of sensors were taken in, and based on the values the processing will happen, and decisions will be taken, and the control action will be invoked. So this is the concept of Industry 4.0. This involves, you can see here very clearly, this involves the wireless connectivity and the online monitoring and control. So this Industry 4.0 describes the trend towards the automation and data exchange in manufacturing technologies and processes, which essentially include cyber physical systems, Internet of Things, industrial Internet of Things, and all cloud computing, cognitive, artificial intelligence, and smart manufacturing and smart factory. So when you see the leveraging Industry 4.0, that is challenges and opportunities of Industry 4.0, you can very well see that different factors influence this. Say, for example, authentication and fraud detection, and location detection technologies, mobile devices, IoT platforms, multi-level customer interaction and customer profiling, big data analytics and advanced algorithms, smart sensors, etc., with a stress on digitization and integration of vertical and horizontal value chains, and digitization of product and service offerings, and digital business models and customer access. So these are the three key points which are very important for Industry 4.0. And the different challenges is, say, development of equipment for each and every point is very important, and advanced human machine interfaces also need to be made. So when we get into Industry 4.0, the user interface is very important, which makes certain flexibility in the automation, and also storing the say, having a perfect database for working further or decision making will be happening. So the four main components of Industry 4.0 is one is a cyber physical system, Internet of Things, smart factory, and Internet of Services. When we get into cyber physical systems, there are three phases that are available. So the identification and integration of sensor actuators, and then development of sensors and actuators to allow the machines to store and analyze the data. And multiple sensors and actuators are networked for exchange of information. So when we see here the cyber physical system as a whole, you can see that this is comprising of three C's. Though we have the information with us, that information will be used to compute and control and communicate. So these are the three C's which involve in cyber physical systems. When we when we want to use the information for computation, and whatever the computed value, if I want to use it for control, or it need to be communicated to the remote end, it can be done through communication or control based on the requirement. So when we see the definition for cyber physical systems, it is a system of collaborating computational elements controlling the physical entities, which are say, whose operations will be monitored, coordinated, controlled, and integrated by computing and communication core. So both the computation and the communication core will involve in cyber physical systems. So when we see this diagram, we can come to a conclusion on cyber physical systems. There exists a physical state. From the physical state, we'll be getting the information, we'll be deriving the information, and the information which are derived, based on it, a particular decision will be taken, and those decisions will be put up in action. So these actions will make a change in the physical state again. So the change in the physical state will be again the information from the physical state. Whatever the change that has happened will be derived, will be taken for decision making, and action happens based on the decisions. So it goes like a cycle here in the cyber physical systems. To build this cycle, we need, say, it comprises of digital, analog, physical, and human components engineered for function through integrated physics and logic. So this cyber physical systems involve more, different areas of, areas of the technology, say, right from the sensors till your communication comes into picture here. So the examples for it would include smart grid, a self-driving car, a smart manufacturing plant, and an intelligent transportation system, or a smart city, an Internet of Things, which has the instances connecting new devices for new data streams and applications. So when we see here, the cyber physical system play a very important role in the development of different applications. So we'll see the examples of CPS, that is cyber physical systems, which are not instances of IoT. We know that cyber physical systems from this slide, we come to know that cyber physical systems include even Internet of Things, a portion of Internet of Things, but still we have certain examples which deviate from IoTs. So the examples of cyber physical systems which are not instances of IoT are something like say Segway scooter, or a smart spoon enabling Parkinson's patients to feed themselves, or an autonomous vehicle operating without a wireless connection outside the vehicle. So it goes like this. So these are certain examples which are CPS, which cannot, which will not come under the IoT concept. So Internet of Things, when we get in, it enables the objects, machines, and sensors to communicate with each other, as well as human beings to work out solutions. Similarly, the integration of such technology allows objects to work and solve problems independently. And IoT can be defined as a network in which the cyber physical system cooperate with each other through unique addressing schemes. So to build your IoT, Internet of Things, the concept of cyber physical systems is very important. That's why I started with cyber physical systems. So the cyber physical systems and your IoTs are two different areas where your CPS would be like a subset that is going to be available inside your IoT. Okay. So when we get into the Internet of Things, as such, when you see, it is going to hold, say, 4 different portions in it. The embedded system, then we have sensors, then we have actuators and radio interface. This embedded system is going to play a very, very important role. It is something like a brain in your Internet of Things. So the embedded system is going to hold, is going to get all the inputs from the sensors, and based on the values that are obtained from sensors, it will try to process it and take decisions based on the values, and the decision will be conveyed to the actuator, and the actuator will try to work accordingly. So these actuators might be even at remote location. So for that, if the radio interface, a proper radio interface based on the level of communication, we need to use a proper radio interface with it. There comes your Internet of Things, which holds 4 different components. So as you see here, this Internet of Things, we see that embedded system is going to play a very, very important role in the Internet of Things compared to the other 3 components. So see, for the sensors, anyway, the decision making is going to be by the embedded systems. Only the sensors are going to give certain inputs, and the actuators are going to execute your output. So the embedded system is going to be the prominent block, which is playing an important role in Internet of Things. So we'll be looking at embedded systems here. The conventional definition The conventional definition for embedded system holds, like, say, it is the combination of hardware and software which is developed for specific application. The same concept holds true till now. So we'll take up the same definition here also. It is the combination of hardware and software which is developed for specific application. So when we see the characteristics of embedded system, it is a single function, tightly constrained, reactive, and real time. So it executes a single program repeatedly. The same thing can be told in a different way. It says that it executes a single program repeatedly. I would say that these days you can see that it holds so many number of programs available, but only one program will be executed at a particular point of time. So it is a single function, but only difference is it holds so many number of programs, and one program will be executed at a particular point of time. And obviously it is tightly constrained because it has to follow, say, the concept of compatibility, then low power consumption, and the performance wise it should be say fast and reliable. So these are the three main constraints which we see for any system, which also true for the characteristics of embedded systems. That is, it is tightly constrained with respect to the compact nature. The area occupied by the circuit should be less. The power consumed by the circuit should be less, and it should be very fast, and it should hold so many number of applications. If at all it is required, it need to it need to accommodate all these applications in it together. And the third point is reactive and real time. It should continuously react to the changes in the system's environment. So there should not be any delay. There should not be any delay in computational. In your computational time, the computational time should be very, very less. So the computation of results should be without any delay. We take an example here, a digital camera chip. You can see here so many number of processors, controllers, and the peripheral interfaces are available. When we analyze this for the embedded system, it is a single function because this will work always as a digital camera. And obviously we look for the constraints like the area occupied by the circuit should be less, the power consumed by the circuit should be less, again it should be fast enough to work on, and reactive and real time. These days, actually I wrote here sometime before, I wrote here to a small extent it was written. Now these days, say looking at the versatility of a digital camera, you can't write it as a small extent. You need to write only as a to a very good extent, because even in the moving environment you can capture the pictures very clearly without any blur. So it is reactive and real time. So what do you mean by a real-time system? So this says that a system which computes, which executes a particular program with a minimal response time, then we call that as a real-time system. So as a primary objective, the computational time should be very less, and if it is not going to meet out that particular deadline, then the entire system might fail to operate properly. So this is going to be your real-time system. And when we see the different types of real-time systems, we see two types of real-time systems. One is soft real-time system and hard real-time system. The definitions are given. I would like to hear from any one of you on examples for soft real-time system and hard real-time system. Can anyone give me an example for soft real-time system and hard real-time system after going through the definition? So the soft real-time system computes output response as fast as possible, but no specific deadlines that need to be met. But your hard real-time system uh, is going to compute the response. Sorry, I mean compute the values and give the response, but it need to it need to meet out the deadline. Otherwise, this entire system will fail. Okay, so this is going to be the uh, uh, say hard real-time system. Uh, so the examples, can anyone give me an example for soft and hard real-time systems? Okay, so the soft real-time systems example which I used to quote here is uh, say your washing machine, where you might be knowing that it works. Say it washes the clothes within a specified time, say a time of say 50 minutes. But when it exceeds that particular time, still there won't be any much impact on both on environment, or the system is not going to fail. Okay, so it computes the output response, but it tries to make it as fast as possible, but it doesn't have actually a specified deadline. Even if it is not going to meet out the deadline, there won't be any huge impact. That's your soft real-time system. When we go with hard real-time systems, I used to tell the extreme example of a controller which needs to control the fission process in a nuclear power station. If it is not going to meet out the deadline after a computation and say action, the values that need to be conveyed to the control unit, if it is going to be less, I mean, if it is going to be delayed, then in that case, a huge impact will be there. And not only the system is going to fail, even the impact on environment will be high. So that we take it as a hard real-time system here. There are three key embedded system technologies which play an important role on, say, the influencing the embedded systems: processor technology, IC technology, and design technology. So when we get into design technology, there are two sets of design, as you know. I think many of you might be even working on the same area which I'm talking about right now. Uh, uh, so it holds two sets of design. I mean, two sets of designs. One with the help of the programming languages like say C, C++, Java, Python, or any other programming language of your choice, with a target device like a microprocessor or a microcontroller would be taken. So these programming languages will be converted into assembly level instructions. In turn, it will be converted into machine level instructions, and it will be taken into the target microprocessor or a microcontroller for a specific action. So this is one way of designing. The other way of designing is use of hardware description languages. So any one of the HDLs will be used, say VHDL or Verilog HDL will be used for say for designing any particular circuit, and it would be converted into the logical circuits and through the logical synthesis, and it will be taken to the target hardwares like programmable logic devices or field programmable gate arrays, or in turn it can be made as an application specific integrated circuits. So these are the two sets of design technology which is available. When we get into processor technology, we have three sets of processors. One is called general purpose processor, an application specific processor, and third one is single purpose processor. We can see the difference here. Though there is not much difference in controller and data path unit, the memory, the access towards the memory, access towards the content, access towards the program is going to have a change. So when we go with general purpose processor, the user will have a say control and full usage of full access of program memory and data memory together, and he can read, write, do all kinds of operations on program memory and data memory. But when we get into application specific processors, there will be a limitation on access towards program memory. The user can read all the programs which are stored in the program memory, but the modifications cannot be done by the user in the program memory. But some small programs can be stored in the data memory along with the available data. So that is your application specific processors. The program memory and data memory also will be bit limited here compared to the general purpose processor. When we come with single purpose processor, you can see that there is no program memory available. You can see here the data memory alone will be available. As the name suggests that it is going to be for single purpose. So the program also will be stored in the data memory itself along with the data. So there is no requirement of a dedicated program memory here. So I'll give you some examples for these three. Say for general purpose process, you can take the conventional say Pentium processors, or say whichever we had for say general applications, like say whatever we learned in early days, say 8085 processor or 8051 controller can be taken as an example here for general purpose processors. For single purpose processor, it will be used as a co-processor or an accelerator in the digital units, and which doesn't have any program memory here. And when we come to application specific processors, it will have an optimized data path and special functional units. And when we see, or when we want to appreciate the difference between the general purpose and single purpose processors, you can see here we can take the same digital camera chip, and the microcontroller which resides at the center part of your digital camera chip can be defined as a general purpose processor, because when we take out this microcontroller and use it, when we deploy it for some other application, it will work accordingly. But your single purpose processor, say the DMA controller which is given here, even if you take out this DMA controller and put it somewhere else, it will work only as a DMA controller. You can't modify the purpose for which that particular controller is developed. So DMA is a direct memory access, as you know. So it does only that operation of direct memory access, the control of access towards the memory without the intervention of the microprocessor to which the memory is attached. When we come to IC technology, as you see here, the IC has got reduced to a very good extent, and we have say in early days in say 8085 or 8051, when you see the size of the processor or a controller would be of the size of a finger. Now these days the microcontroller unit occupies something like say a 0 PCB space, which has more versatility compared to the conventional processors or controllers. So when we go like this has happened just because of the development in the IC technology. As you know this, say In 80s, it started with say 2-micron technology, and as it goes, these days you can see that even in research you have say in digital ICs, it is going till say 22 nanometer or a 10 nanometer or even to the level of 7 nanometer under research. It is there. So the discrete ICs have a very good good upcoming technologies have come up for discrete ICs. When we compare with analog ICs, it is a bit slower because of the MOSFETs working on all the three regions of operation. So it takes a time to evolve different technologies beyond 65 nanometer. So this says that the IC technology had played a very important role in uh, miniaturizing the circuits and also the power consumption, reducing the power consumption. So the embedded system enabled applications you can see here. It is taken for different sets of applications like utility metering, like electricity meters, gas meters, flow meters, smart meters, etc. Similarly, sensors and security and energy harvesting, consumer electronics, portable medical equipment, then personal health and fitness, etc. Uh, so it all goes like this. When we see for the power engineering, when you want to make a grid to be a smart grid, then we need two components coming into picture along with the robust power system. The robust power system is available to make this grid to be a smart grid. Then the use of embedded systems play a very important role. We see here on one side we have a robust power system, and on the other side we have a sophisticated communication technology available. So to interface these two, we are in need of embedded systems. So to create an interface between the communication technology and the uh, robust power system, we need the use of embedded systems. So here we can see the community-based microgrid. For see this controllers. I mean these controllers which are required here would be used for effective power conversion and also for interfacing with the communication technology. So when we see here the community-based microgrid, we would be having so many number of energy sources, energy storage elements, and along with the different types of loads. So now if we want to have a proper energy management in this community-based microgrid, then we might require an effective power conversion with the help of digital controllers. So from the solar, if we want to convert the energy, solar energy into electrical energy in an effective manner, then we need a proper controller here to operate with the maximum power point tracking algorithm. So this maximum power point tracking algorithm, which is going to reside inside the controller, will try to effectively convert the solar energy into electrical energy. So this happens with the help of a digital controller. Similarly, when I want to have a proper energy management, as you know that at all times your solar energy is not going to be available. So when the solar energy is going to be in, when there is a shortage in solar energy, then the energy that is stored in the batteries or the dependency on conventional energy, conventional power generation units would be used. So to have a proper energy management, we might require another controller which would have an interface between the sources and the load. So based on the availability of sources, the load will be connected, and similarly based on the requirement from the load side, the energy will be produced from the sources. So these two can be done with the help of a proper energy management system. So when we see an architecture of any sensor node, which is going to have a microprocessor or a controller, a communication module, and several sensors will be there to get interfaced, so that the status of the particular system can be easily identified and decision can be arrived and communicated. So when we see here, this is a typical wireless sensor node, which is meant for an effective lighting system. When we see here, we have interfaced two sensors. One is a light dependent resistor, and the other one is a PIR sensor, that is pyroelectric infrared sensor, which is also called as human detector or motion detector. So when we see here, we have two sensors. The controller will get the input from both the sensors at all times, but the controller will decide which sensors input need to be used at a particular point of time. So when we see here, this LDR, the inputs of LDR will be taken into effect between 9 a.m. and 5 p.m. and the inputs of PIR sensor will be taken into effect between 5 p.m. and the next day 9 a.m. So which says that during the office hours, during the working hours, LDR will play an important role, and during non-working hours, PIR sensor will play an important role. So based on the external lighting during the working time between 9 a.m. and 5 p.m., based on the external lighting, the internal lighting will be adjusted with the help of the LDR sensor, and for that the microcontroller would be helpful. And similarly for during the non-working time, the PIR sensors, that is human detectors, will identify where and all the human presence is there. So based on that, the lighting will be say on or off, and it will be effectively managing the power consumption required for lighting in a particular area. Here you can see that the microcontroller is available separately, that is MSP430, and for communication we had used a controller CC2500. This was in, say, this has happened a long time before, but these days they integrated MSP430 along with CC2500, and they made as a single controller which holds both control and communication node, and they named it as a CC3200. So the CC3200 will be used for both control and communication as a single node. When we see the energy harvesting and wireless RF transmitter system here, through the power line, see over the power line, whatever the stray magnetic energy that is available will be harvested via inductive coupling, and those say that energy will be used to power the wireless RF sensor node. So with the help of a power management unit, this would be possible. So this power management unit, when you see the internal components of power management unit, it will be a rectifier, energy storage and supply circuit, and linear voltage regulator will be there, which is going to say effectively convert the energy, and it's going to feed the wireless RF sensor. So when you see here, with respect to smart grid, there will be a good, robust infrastructure. I mean, electrical infrastructure would be there. and a sophisticated communication infrastructure would be there, and a proper computational and decision-making system need to be developed. And for different applications of smart grid like EV, electric vehicle charging coordination, or remote monitoring, or appliance coordination, etc. But at different levels, at all the different levels, we need to have a proper security to ensure the proper operation of the each module. So when we get into the different smart grids, here we are having the hybrid power systems, which combines the multiple sources to deliver an non-intermittent electric power to the load. So we'll be having a conventional generator unit along with the renewable energy sources. So for a proper regulation and conversion of energy, the controller will be used, and for the proper energy management also, the same controller can be deployed. When we see the internal diagram of smart meter, it is going to sense the value of current and voltage, and it is going to process the power and energy using the processor. And based on the different digital interfaces, like Ethernet, Zigbee, or PLCs, that is power line carrier communication, any one of it will be used for communicating the value which is processed using this particular processor. So this can also happen with the help of different types of networks. It might be a home area network, or a local area network, or a wide area network based on the application. So the practically deployed smart meter is shown here. Similarly, here one more. I would be talking about the one or two case studies which we did as a project after we look in this Internet of Things in smart grids. So you can see here the architecture of IoT in application of smart grid, where the perception layer, network layer, and application layer would come into picture. Say the wireless sensors, RFID, and cameras would occupy this perception layer, and the network layer would hold different communication technologies, say Zigbee, Bluetooth, PLCs, Wi-Fi, etc. And the application layer might hold different sets of application like fault detection, or a demand response, or electric vehicle charging, or for smart homes, or smart energy conversion, etc. And when we look for Internet of Things for an effective energy conversion and also for energy management, then we call that as an Internet of Energy. So it interacts too many number of sources, and it integrates it, and based on the available value of power, the different loads will be catered. So this concept, we call it as Internet of Energy here. So one more Internet of Things in smart grid is the consumer can become, the consumer is the person who is going to consume the power from the grid. The consumer can become a prosumer, that is a producer plus consumer. So the consumer can say deploy more number of photovoltaic systems over the rooftop, and the consumer himself can become a producer, and he can feed that particular power that is produced into the grid, and thereby he will be getting a proper say balance between the power that is utilized from the grid and the power that is fed to the grid from the power production from his rooftop. So this happens. Similarly, the integration of renewable energy is highly required. This needs the IoT technology, which uses wireless sensors to collect real-time weather information to help in predicting the energy availability in the near future. So this plays a very important role. The weather forecasting, or say through the machine learning concepts, or by getting the real-time weather information, plays a very important role in deciding, or say deciding the power management concept. When we again look for online monitoring, in early days, it is very difficult to have a self-healing concept in the smart grids or in the grid itself. When we make it as a smart grid, the deployment of Internet of Things improves the quality of smart grids by self-healing feature. That is, when a particular portion is going to get a breakdown, or due to the unforeseen situation, if some fault is going to occur, that particular portion alone will be islanded, and the rest of the system will be operated with a stable, without any problem in the power. So this concept, we call it as a self-healing mode. So the self-healing mode is possible because of the use of IoTs. So one case study which I'm taking here is FPGA-based SOC estimator and constant current charging and discharging controller for lead-acid batteries. So the same thing can be deployed. Same concept can be implemented for lithium-ion batteries also. So here the state of charge is estimated based on say the measurement of available of amount of charge, and the accurate estimation is the goal to improve the lifetime of battery and reliability. There are different methods of SOC estimation available. Say one such as a Coulomb count method, then open circuit voltage method, etc. Say we deployed here the extended Kalman filter algorithm. So this EKF algorithm is more effective even compared to the Coulomb count method, which takes into account the concept of aging of the batteries. So when the aging of batteries occurs, the charging and discharging pattern of the battery is going to get changed, which also will be taken care by this EKF algorithm here. So this EKF algorithm is implemented inside FPGA along with the proper charging and discharging control action. So the control algorithm was implemented using FPGA, and the interactive GUI is also created to have say on and off, and also to change the level of charging and discharging that can be monitored using this particular screen. So we get the estimated SOC, you can see here, and the implemented hardware is also shown here. The same thing can be implemented for lithium-ion battery SOC estimation. Not only SOC estimation, they say one more concept in batteries, that is state of health. So the state of health and state of charge can be analyzed with the help of the controllers. One more architecture which I am taking here is a standard hybrid EV power and control architecture here. In electric vehicles, we'll be having a DC to DC converter. Similarly, a motor inverter and a generator inverter would be like this. So for all these three, say converter and inverter control, we might need a specific, dedicated microcontroller units like this separately. 3 sets of microcontroller unit might be required. So to improvise this, architecture, we can go with a single FPGA which holds all the three control aspects. So the converter and the inverter control concepts will be implemented in single FPGA, and the single FPGA will try to control all the three units of say converter and inverters. So the benefits of FPGAs in hybrid electric vehicle or electric vehicle applications is the performance improvements. So it will have a tighter control loops and faster switching speed for improved efficiencies. Similarly, continuous algorithm improvements for better performance. Similarly, when we go with differentiation while lowering the costs, the custom algorithm in model based design technologies for better drive field and efficiency, and integration of functions into fewer components, and long product life and functional safety is possible. When we expand this differentiation while lowering costs, you can see that the FPGA enabled enabled electric vehicle system will have a faster switching frequency when compared with the conventional one, and it also reduces the size of the passive components by 5x time. So the inductors and capacitors which are used for switching, due to the switching activity of FPGA getting increased by 5x times when compared with microcontroller unit, the size of the passive components can also be reduced by 5x times. So this is shown here in this diagram. You can see here in the conventional system, we have the inductors and capacitors of higher size. The same if it is implemented with the help of FPGAs, where the FPGAs are going to be 5x faster. This makes the inductor and capacitor size, the use of inductors and capacitors at a 1/5 size compared to the conventional system. So it is also shown here. So when we use microcontroller unit based 10 kilohertz switching with IGBT, we might be using the inductor and capacitor of a certain size, which can be reduced to a level of, say when we deploy it with the help of FPGAs, the switching frequency goes high, and the inductor and capacitor size can be reduced considerably. Okay, so when we again see this Internet of Things, and as I said, the embedded systems play a very important role here, along with the sensors and actuators. It implements an effective system through the radio interface. The IoT concept is very well deployed for any application. So it connects everything: physical objects, living organisms, persons, concepts, services, resources. Anything that is interesting from the perspective of an application will be connected together. So there are different smart objects, devices, things are available, which will be, say, integrated for a particular application. So different types of sensors. In the environmental point of view, if you see a temperature sensor or a CO2 or pressure or ambient light sensors, all these things would be used for, say, for constructing any environmental monitoring unit. Say when we want to convey or communicate the information that is gathered from all these sensors, then we might require a proper gateway. So we'll be using any one of the communication module for it. And to collect and segregate the the data which is sent from different sensors, we might need an effective control unit also. So the sensors and the actuators, you can see here different sensors and actuators which are shown here. Say the flow sensors, and force and load, torque sensors, pressure sensors, then level controllers, then acceleration or tilt sensors, machine vision or optical sensors. Then we have position, presence, and proximity sensors, the motion detectors, velocity, and to detect the velocity and displacement. Similarly, for temperature, humidity, and moisture sensors, mainly required for agricultural purposes. Then acoustic and sound and vibration sensors. Similarly, gas and chemical, different types of chemical sensors that are required for identification of concerned chemicals. So we will be using these sensors and actuators in as part of IoT. So when we want to get connected, we'll be using any one of these networks based on the requirement. So we'll start with the personal area network for a very short communication. Uh, we'll extend it to local area network if that is going to be for a particular locality or a community. Then we'll extend that further with a metropolitan area network, and still if it is required in a higher range, then we'll go with wide area networks. So this goes like this for the different levels of communication. Mm. When we get into the smart city, as I told that this industry 4.0 is going to concentrate on the concepts which are not listed under industry in a conventional manner. We see that the smart city is also going to have sensing, networking, analysis, and control. So when we see main parts of the smart city is sensing and networking, when we see that networking is to communicate and also for resource allocation, and sensing for measuring, estimating, and reporting the values. So this is the picture which shows the city of Stockholm, where the smart city concept has been implemented. You will be having this sensing, networking, analysis, and control part will come into picture very effectively here. So the smart cities can be identified along with 6 main axes or dimensions. It includes smart economy, smart mobility, smart environment, smart people, smart living, and smart governance. So these are the actual factors which influence the smart city concept. As you see here, smart economy is required to manage the the expenses for making a perfect decision making and control. And similarly, smart people, the literacy rate of the people should be increased to a higher extent. Thereby, the concepts which are implemented for smart city will be maintained by the people in an effective manner. So IoT in smart cities, when you see IoT in smart cities, it includes smart wearables, then smart mobility. The vehicle to vehicle communication is made possible to avoid the accidents, and smart parking. As you see that parking lots, in certain cases we won't be identifying where is the vacant space, which will be displayed in the entrance itself, so that you can park your vehicle at a particular location, and you can without any hitch you can take the vehicle also out when you want to come out of the mall. So the water quality and the water distribution will also be, I mean, can also be made in a digital monitoring way. And apart from that, we have the traffic priority, then smart grids, as I talked before, and security and surveillance will come into picture. So when we go with smart buildings, any portion of your house will be, can be made smart along with self-sustained power production. So at the rooftop, you can make use of the power production using solar panels. Similarly, at the entrance, you can make use of a proper security and surveillance through the cameras, and you can store the database can hold the person who are all known to you is coming to your house can be stored, and thereby you can identify who has come at the entrance of your house, and whether to allow them inside or not can be decided. And in addition to it, you would be knowing who, even in your absence, who and all has come, and it is a perfect security that is being created with the help of the camera and a closed circuit TV surveillance. And smart kitchen, as you know, that different types of units can be deployed in the smart kitchen, and living room, again, different appliances and gadgets can be deployed. So this makes a building to be smart. Uh, Apart from this, as I mentioned before, something like a zero energy building, you can create a zero energy building where the energy produced in the building will be used by the building itself, so that there won't be any power, an extra power consumption from the outside world. Autonomous cars, as I mentioned, vehicle to vehicle communication is very important to avoid the accidents or to give a proper security for the vehicle. We'll be using this V2V communication. And unmanned aerial vehicles for say for used by different vendors also for distributing their products to at different places. They use this unmanned aerial vehicles. Smart grids, as I mentioned, right from generation till the distribution and consumption, the controllers will be deployed, and the concepts of IoT is implemented to make a normal grid to be a smart grid. The environmental monitoring, as I mentioned before, CO2 or a temperature or humidity or pressure monitoring, all these are being carried out to identify the health of the environment, and thereby they'll try to deploy the pollution control, etc. The digital monitoring of water supply is being even done in many cities of Tamil Nadu. So as a part of smart city concept, they do this digital monitoring of water supply also. So in near future in Trichy also, they'll be monitoring how much water you consumed in your house, and they'll put a meter to charge your water consumption. So parking, as I mentioned before, the smart parking can be deployed in an effective way, so that there won't be any hitch in parking your vehicles. Smart bins, this is one of the very important one. As you see that in the normal smart city concept, they put at different types of bins at different places, but still the junk items which are dumped in that particular bin will not be cleared at regular paces. To enable that, if the bin is say filled with 60 or 80 percentage of its size, then this smart bin would indicate to the scavenging center, so that the scavenger, I mean the clearing person, might come over and clear this bin and make it clear, make it clean. So this is one more aspect of your smart city, where keeping all the roads and places to be very clean and tidy. So the diversified applications are there uh, because of the use of IoT. Um, so we have irrigation controller, or infotainment, or energy monitoring in home consumers. And similarly, in transport and mobility, we have smart parking, package monitoring, or insurance adjustments, or shippings, traffic routing, etc. And coming to health and body care, we have elderly monitoring, remote diagnostics, equipment monitoring. Then coming to the infrastructures, we have a smart energy management. Then we have structural integrity, emergency alerts, etc. Coming to the industries, we have a good smart grid, waste management, electrical distribution, and surveillances. So, so the city vision will hold right from street light management till fleet management, and from the access control towards the lighting control. All these would include in the smart city vision, which involves different types of controllers and the concept of Internet of Things. So the need for basic research of IoT, this includes three main areas. One is systems and control. Then we have machine learning and networks. So these three areas will play a very important role on IoT's research. So when we see when we want to develop a particular system for weather monitoring, then we need a proper system for say an algorithm for going through it. Similarly, the machine learning concept and networking also comes into picture for that particular system. So for any system, for that matter, these three are the main areas in which the IoT relies on. So with this, let me complete my lecture here with this set of words which are given by Swami Vivekananda and India and Her Problems book. The only true teacher is he who can immediately come down to the level of the student and transfer his soul to the student's soul, and see through and understand through his mind. Only such a teacher can really teach, none else. So this was, as I said, this was told by Swami Vivekananda and on India and Her Problems book. This has inspired me to become a teacher. So I used to display this particular wordings at all my lectures. I don't know how far I did justice to the topic, but still, this is the concept for reaching the true teaching, to become a true teacher. Any queries? If you are, if you have any queries which comes in afterwards, also you can send through the mail, so that I would be happy to reply you. Okay, thank you for patient listening, and I thank the management of IIT Trichy for giving me this opportunity, Professor Sitaraman for having involved me in this particular workshop. Thank you all. I wish
Thank
you
you,
all
sir. Sir Sitaraman, sir. Thank you, sir.
Thank you, sir. Thank you. Thank you.
Thank you, sir. Yes, sir. Yes, sir. Yes, sir.
Shall I close it?
Next session will begin by 2:30 p.m. Participants are requested to fill the attendance form posted in the chat box. Thank you, Professor, for your valuable information. The session was very interesting.
Thank you. Thanks a lot.